Okay, we're going to talk about some impulse questions now. If a car has a mass of 2,000 kilograms and has a velocity of 12 meters per second, is hit by the force described in the below graph, find the final velocity of the car. And here is the graph. Okay, so I'll do this one. We realize that we've got a mass of 2,000 kilograms. Our initial velocity is 12 meters per second, and it is west. And then we are not really given much else except for this graph. Okay, and so what on earth is up with this graph? So let's see what's going on here. Time, and this is the highest maximum force that you achieve is do it like that, is 15,000 newtons. And it is north, actually. So that's an important little feature there. Okay, well, we know that if this is time, and this is 0.7 seconds, we know that impulse is equal to force times time. Force times time, anytime you're multiplying two things and you've got them in a graph, you can actually, this is force and this is time, you can actually find the area of the graph, and that's the same as geometrically, it's the same as multiplying. And so the area of this thing here is 15,000 times 0.7 divided by 2, because it's a triangle. Okay, so it looks like the force is applied, and then it reaches its maximum, and then it's sort of unapplied as well. Okay, because this is all sort of force in here. And so, yes, so the area equals impulse, and the area of this thing is 15,000 because it's the height, times base. The base is 0.7, so it's the impulse is 15,000 times 0.7 divided by 2. And let me just get that here. 15,000 times 0.7. Enter, and then I'll divide that by 2. I'll get 5,250. And so that the impulse is 5,250 kilogram meters per second, and that, by the way, is north still, because it takes on the direction of the force. And so if I'm going to convert these, this is 90 and this is 180. North is 90 and west is traditionally 180 according to the calculator. And so I'm going to need that information here, because I also know that impulse is equal to not only force times time, but it's also equal to mass times initial or final velocity minus initial velocity. Okay, and it looks like I've got initial velocity, I've got impulse, I've got mass. I'm looking for final velocity. Bang, that's what I'm looking for. And so if I do some algebra here, I divide by mass, so it's impulse divided by mass, and then if I add initial velocity, that's going to be my final velocity. And so that's what I'm doing here. So it's impulse, which is 5250 kilogram meters per second divided by 2,000 kilograms. This is nice because the kilograms cancel and I'm left with meters per second. Bonus, because my initial velocity is 12 meters per second. And so this is equal to velocity final. Let me just do 5200. Oops, what is it? 5250 divided by 2,000. Not really sure what that's going to be. 2.625. 2.625. And again, this is impulse, which is at 90 degrees. I forgot to write these down. And this is at 180 degrees. So this is 90 plus 12 at 180. I dropped my meters per second for just a moment. And so now I'm going to just do this in a vector addition chart. You just add these, and that's the final result. Okay, I won't do a vector addition chart. So, next one is for impulse. It says that Robin Hood shoots an arrow 300 grams at a wooden target and is securely fastened to the ground. The arrow hits the target at 120 meters per second and penetrates 4 centimeters into the target and then comes to a stop. I didn't mention that. And so I ask several things, A, B, C, and D. Okay. It says Robin Hood shoots a 300 kilogram arrow, or 300 gram. I'm going to just write my mass as 0.3 kilograms, just because we want to be dealing with kilograms, because I'm dealing with newtons and things like that. As soon as you get into impulse, you really want to be in kilograms. With momentum, you actually can stay in grams, really. Although you shouldn't, I guess. Anyway, the arrow hits the target at 120 meters per second. So it looks like the initial velocity is 120 meters per second. And then it has a displacement of 0.04 meters, 4 centimeters. And then the final velocity is 0 meters per second because it comes to a stop. It says find the time that it took the arrow to stop. All right, this is going to be a very small amount of time. Okay. We know that it's delta D is equal to 1/2 VF plus VI times delta T is a kinematic equation. I know VI, VF, delta D. I can find T is equal to 2 delta D divided by VF plus VI. Okay. That's the time that it took to stop. I won't figure that out unless we need it a little later on. You just do 2 times, that divided by 120. Actually, I can just do that real quick. 0.08 divided by 120. Very small, 0.0006. Actually, I'll round it up because it's 0.0067. All right. Part B, find the impulse imparted to the arrow. Okay, so impulse, it turns out, is equal to mass times Vf minus Vi. And so I know the mass, I know the final velocity and the initial velocity. Final velocity is 0, by the way. And so it turns out that the impulse is mass times negative Vi, actually, which is 0.3 times negative 120. So what is that? 3.3. So 36. 0.3 times 120. Yeah, 36. And it's negative. Why is it negative? Because it was actually slowing down. So it was a negative impulse, a negative change in momentum. Remembering that impulse is change in momentum. Part C, find the acceleration of the arrow. Acceleration is delta t, Vf minus Vi. Okay, again, Vf being 0. Wow, this is really convenient. Vf is 0 so much. And so it's actually just negative 120 divided by 0.0007. And this looks like it's going to be a pretty mega size acceleration here. 120 divided by 0.0007. It's 170,000 meters per second, and it's negative. Oops. Negative. That's because it's slowing down, and it's meters per second squared. And that's really high, but that's understandable. I mean, this is an arrow hitting a target, and it slows down in virtually no time at all. Find the force applied, the average force applied to the arrow. I say average because it's the applied force, but it's sort of on an average over this entire time interval. And we could make a graph of it. But this would be part D. Force applied is change in impulse is equal to force divided by time times time. I already know the time. I already know the change in impulse. And so the force applied, I'm running out of space here, is divide by time. So it's negative 36 divided by 0.0007. And it's a negative force as well. That's nice. Because it's slowing down. And so it's a negative 36 divided by 0.0007. And we get, on average, it's about 51,000 newtons. All right. So that's some impulse questions.